Let's talk about basic classification models, in particular for binary classification. So a binary question represents the basic decision making, yes or no, true or false, and so forth. So how do we build a model to answer basic questions of these? In particular, how does a model learn to train data to make predictions about yes versus no? Let's use a simple collection of data here, um, a collection of shapes with different width and height. And this is a collection that we can use to illustrate the basic point of classification, whether a shape is standing versus lying. So let's look at the data here. And again, it's a very small collection with only a few variables. The width, the height, and the class about standing or not. Okay, so intuitively, when we look at the shapes here, the ones that are taller, that their height is greater than the width, it appears to be standing. So the classification here is that it stands. And so let's look at the data here. And the basic observation you can see is that whenever the width is greater then the height is not standing. It appears to be lying. And whenever the height is greater than the width, it is standing. So whenever width is less than the height, this leads to standing. And we can check another data point here. The width 2 is less than 4, so the answer is yes. Okay, so whenever W is less than H, you have a yes answer. And so this looks like a very simple question for human eye. And it is maybe tempting to kind of hard code the rule and just to say, okay, whenever the condition is height greater than width, we want to make the prediction of yes. And otherwise, we're going to make the prediction of no. But this defeats the purpose of a data-driven machine learning model because it's not for us really to hard code the rule, but it is for the machine to find out from the data what the rule or condition should be. Because it may be easy for us to do that just by looking at this small, simple data set. But when this data gets bigger, it is impossible for us to do it manually with massive data and more complex relations. And so we should consider other strategies by which related rules and relations can be captured from training data and then used in predictions. What are the potential strategies can we use? Let's look at a few proposals here. So, the easiest approach to learning is not to learn at all. And so if we are going to use machine learning to help us mine data and mine relations and rules from the data, perhaps the best way is not to really understand what the data is and simply just memorize all the materials or data given to the machine. Okay, I'm not saying it's the best way, but it's the simplest approach. And so we refer to this as the lazy learning because the learning does nothing except for having a copy of everything. So in machine learning, a lazy learning method does not build any model, but simply remembers all the training instances. Now, how does a lazy learning algorithm predict on the test instance? During test, the method will search its memory with all the copies of training data and finds the most closely related instances to the test and predicts the answer based on those closely related instances. And we have a term for those closely related instances. We refer to them as the nearest neighbors. And a classic lazy learning algorithm is the k-nearest neighbor approach, which makes predictions based on the k closest training instances. So how does the algorithm find out which ones are the nearest? And of course, it takes a particular distance function or similarity function to find out which ones is the closest, which ones is the farther away. And so an example of such a distance function is the Euclidean distance, which is the straight line distance connecting the endpoints of two data instances, U and V. So a Euclidean distance formula is looking like something here. So between data points U and V, the distance is simply the square root of the sum square of the differences on each individual dimension. Now each dimension is about a variable or attribute. And so depending on how many variables the data has, you have the number of dimensions, or m. M here is the number of dimensions or variables that you have. So back to the data that we have about the shapes, right, with the height and the width. So if we use width for the x dimension and height for the y dimension, we can plot the data on this two-dimensional space, and it's something we can visualize because there are only two dimensions and two variables here. And so when we plot on here, we have the data here, we can measure how far each data point is from another using the Euclidean distance. So this is one way we can measure the distance, just by drawing the straight line. And we can measure how far they are from one another. Mathematically, if you have more dimensions, more variables, it's also possible to do that. It's the same procedure. Now, with the KNN, the k nearest neighbor approach, if we set k equal to 1, we'll only use the 1 nearest neighbor for prediction. So for example, here we have a data instance here, okay? Let's suppose this is the new shape that we don't know about the classification, and we want our k-nearest neighbor to predict which class it belongs to. Okay, so if we read this particular data point is 4, 7. Okay, so we can compute the distance of this data point to any of the existing data point in the training set. Okay, and we can find out that the closest or the nearest neighbor is right here at this data point where the reading should be 5, 9. Okay, and so the distance between the testing data here and the nearest neighbor, according to Euclidean distance, is simply to calculate the difference on each dimension, okay, on the x or the width, first dimension, take the square, plus the difference on the y, take the square, and then you calculate the sum and take the square root. And so the result of this is that they are square root of 5 apart from one another. Okay, so this is according to the Euclidean distance. And we discussed this in a different lecture about the different similarity and distance functions. And we know that Euclidean distance is actually a special case in the Minkowski distance family. So this is the formula of the Minkowski distance. And you have the parameter p. When p equal to 1, this is the Manhattan distance or the block distance. Think about when you walk, in the streets of Manhattan, how many blocks does it take for you to walk from one place to another? Okay, so this is the block distance. When p is 2, that is the Euclidean distance. And you can choose other numbers of p for different purposes. Now, another metric that is similar to Minkowski distance, but not exactly the same, is it is kind of similar to the Minkowski distance with p equal to 0, but it's not exactly the same. This is actually called the edit distance. So it's basically taking each dimension as a binary variable. And so if there's a distance, it's 1. Okay, if the values on that dimension is different, it's 1. Okay, if they are the same, then it's 0. So you basically, this is equivalent of treating each dimension as a binary variable, and the overall distance is the amount of change in the bits. Okay, so there are a variety of distance or similarity functions. And again, in another lecture, we also discuss the cosine similarity. So it is also possible and sometimes preferable to use cosine similarity in certain applications. So similarity is just the kind of the opposite of looking at distance functions. And so especially in text data, cosine similarity is very effective. So this is something also to consider. But with different similarity or distance functions, we can measure which ones are the closest or nearest neighbor, which ones are the ones that are remote. Okay, so this is what the distance or similarity function can tell us about. As we observed, a lazy learner such as the k nearest neighbor does not actually learn and build a model that can be generalized. Although KNN has decent performances in many applications, it suffers in domains where, for example, test data appear on a very different scale from that of the training data. So if we assume that the class can be separated by a function with certain parameters, then building a model requires identification of those parameters from training data. So surely there are many different ways and different functions that one can choose to model the data. Let's start with the simplest, a linear function. So with the shapes data that we have seen earlier, we have two variables, the width and the height. And here I would like to refer them as the x and y, or v1 and v2. So here, as we observed, the relation between the x and y, the width and height, is actually can be written as a linear function to predict the class, yes and no. So for example, here if x minus y, which is width minus height, if that is greater than 0, then the class is no. And if otherwise, that is x minus y is less than 0, then the answer is yes. Okay, so we see that the linear equation that separates these two classes is x minus y equal to 0, right? Or we can write it as v1 minus v2, v1 for width, v2 for height, equal to 0, okay? Or if we put all the parameters together in this formula just to make it more generalizable, it becomes 0 plus 1 times v1 minus 1 times v2 equal to 0, or it should be w0 plus w1 v1 plus w2 times v2 equal to 0, where the w parameters here are w0 is 0, w1 is 1, and w2 is minus 2. Is minus 1. And this linear equation of v1 minus v2 equal to 0 or v3 minus v2 equal to 0 is a linear function, and a linear function is a straight line on a two-dimensional space. On a higher dimensional space, when you have more variables in there, 3 dimensions, for example, it becomes a surface or a plane. And on an even higher dimensional space, it becomes a hyperplane. But mathematically, they are all part of the family of a linear equation. And so just to make this equation, linear function, really generalizable, we can make it as W0 plus the sum of Wi times Vi, where the Wi and W0 are the parameters to be estimated, and Vi is the data values on individual variable dimensions. And M is simply the number of variables out there, or number of dimensions that you have in the data space. So this is a simple linear combination of the weighted sum of the variable values. Now, how can we find out where the linear function is? In particular, on a two-dimensional space, given two variables, how can we find out where the straight line should be given the data in the two classes in the training data? And so let's start with a very simple strategy using the idea of a centroid. And so a centroid, by definition, is the center of the mass of the group of objects and can be computed as the average of values on each dimension. So again, we use a dimensional space using the variables to represent each data point. And so the centroid of a group of data points in there is basically the sum of values on each dimension divided by the total number of values in there. So it's a very simple function here. Let's look at an example. And so following the equation that we have just seen, and the data that we have in the shaped small data set, we have the blue data point, training data points, 3 data points in particular in the blue class. And we also have 3 data points in the red class, which is the null class. For the 3 blue class data points, the center or the centroid of these 3 data points can be computed right here. Okay, so what you do is basically look at the x dimension, which is the width variable, and compute the average, the mean of the 3 values on the x. And then you also compute the average, the mean of the 3 values on the y dimension. And you get the center of these 3 data points. And likewise, we can also compute the center of the 3 red points as well. So as you can see, the center, the mean of the plus class is the the mean of the values on x and the mean of the values of y. Okay, and so these are the centers for the 2 classes here. And so with these 2 centers, we can identify the middle point here between the blue center and the red center. And the idea here, the strategy here is that if we want to separate the 2 classes, one way we can separate them is that perhaps the border, the separation should happen somewhere in between the 2 centroids. And so we can take the middle point, and there is this dashed line connecting the blue and the red centroids, and we can actually draw a linear function perpendicular to this blue dashed line. Okay, so something perpendicular to the dashed line becomes a linear function to separate these 2 classes, which looks good here. So the first idea is that we need to find where the center is, which becomes a very simple calculation between the two centroids here. Okay. Now, how do we find out which linear function actually is the one that is perpendicular to this dashed line here? Okay. And so we can think of this dashed line as a vector, okay, from the middle point. Okay. So a vector from the middle point to this particular v data point. Okay. And so any data point here, if you think of it as a vector v, and so this vector v is the line here pointing in this direction. And so if you think of this black solid line as another vector u, then mathematically for u and v to be perpendicular to one another, then their dot product, okay, their dot product has to become 0 mathematically. And so with this in mind, let's look at how we can actually find out where the separation linear function should be. Okay, so again, v, which is on the dashed line, can be thought of as a vector from the center point, the middle point between the two centroids of the classes. And so any vector from the point is, if the value of v is v1 and the value of v's value on the second dimension is v2, then this is the vector representation for this vector v. And so next, for any vector to be perpendicular to the dash vector that we observe there, their dot product, as I said, should be 0. So that is v vector and u vector, their dot product should be 0. Okay, and so the result of this is a simple solution here. In the end, we can find out this is the linear function, makes the dot product to be 0. And so this linear function is exactly the black line here, which basically separates the two classes. And so now, given a particular data point, we have, and the reading here is 4, 7. And we try to predict what the class this data point should belong to. Okay, and so with this with this equation here, we can plug the values back into this equation and find out what the result is. Okay, so we plug the values in, and it turns out the result of this linear function is greater than 0. And so we are going to predict this to be positive. This data test instance must belong to the positive class or the standing class. This does work, and we can find out where the linear function is using this central idea. But there is one problem. The central approach is greatly impacted by the density of the training data, where most data instances are, because when we look at the centroid, it's really looking at where the mass is. And so having more data instances with smaller width and height, for example, in the negative class, as shown here, will greatly impact the way in which the data are distributed and will change the linear function to a very greater degree when we use this centroid idea. So this, look at the example here, just a few slight changes in the training data. We have a very different linear function here. And so the centroid-based approach to linear classification is greatly influenced by all data points in the data set and how they are distributed. And so perhaps it's not necessarily the best idea to draw the borderline or to draw the linear function based on the centers or centroids of the data. And there can be perhaps a better way to do it. So later we are going to look at another linear model based on the so-called support vector machines. And that is still following the same idea to find the linear linear function to separate two classes, but it relies on a very different strategy to find out where the linear function is. And so we are going to take a look at that strategy as well.